Welcome. Today's notes worksheet is entitled Properties of Functions. This lesson represents an opportunity to get very comfortable with the graphing calculator and all the features and functions that we will be exploring over the course of the year. So please have a graphing calculator available and find all the particular buttons that we'll be pressing, and let's see if we can put that in the context of analyzing the graphs of functions and working through some characteristics of functions. So let's start it out here. There's an investigation at the top. I came up with just an arbitrary cubic function right here that we'll look at momentarily. And we're going to go ahead and graph that on a very particular window. I'll tell you what this notation means. And we'll go ahead and just see some of the features that we're looking at here, some of the characteristics. And right away, actually, just kind of thinking out loud with this, can you tie A and B together for me? Can you tie C and D together for me? And why not? How about E, F, and G? There we go. That looks good. So everyone, get that calculator if you would. Let's graph. So I go to the y equals, and I'm going to go ahead and type in 2x to the third minus 15x squared, and then a 24x and 19. All right, now I'd like to see this on a particular window here, so hit window for me. And you can kind of see this is going to relate to the three x values on the window, 1, 2, 3. This will correlate with the three y values that you see. And if you have some other stuff, I think you can kind of consider that irrelevant, to be honest. So let's go -2, 6, go by ones. And then I'm going to go from -15 to 35 and go by fives. When you have that all typed in and it's looking pretty good, let's go ahead and hit graph on that. And you can see we've got a nice cubic function right there. As we kind of analyze this graph from left to right, it's kind of going up, comes back down, then goes up again. We could probably put arrows on both ends, kind of an arrow going that way and an arrow going that way, something along those lines right there. All right, now let's see what we have on your paper, and then let's see if we can go ahead and work with the graph. So letter A, it says find the relative, sometimes called the local, maximum of the function. Is it also the absolute maximum of the function? So again, I kind of described the graph. It's going up, going down, going up again. Are you okay with me sort of designating this as what we would call a local max or a relative max? It's kind of a high point right up here before turning back down. Now that's what we're going to find. Is this the highest point on the entire graph? No, absolutely not. If you look at this part of the graph, it's going up to infinity. So there really is no absolute maximum. But there is what we would call a local maximum. And we will be kind of pursuing that piece over the course of the year, and you'll see that in pre-calc and calc as well. So let's go ahead and get it on the calculator. And hit second for me, if you would, that button right there. And everything's going to be under the trace menu, or really, do you see it's the calculate menu. And there's what I'm looking for right here, everyone, the maximum. So let's go ahead and hit that piece. And you have a couple options with this. Notice what it asks us to do. It asks us to find what we would call the left bound. It needs to kind of get a boundary for where that maximum is. What that means, everyone, is you basically have to come over somewhere to the left of this. Now you have two options. You can either scroll, like I'm doing right here, or you can just go ahead and put in a number that's to the left of it. So like, for example, I am to the left, and this would be fine if I hit enter here, but what if I just put in 0, something like that, and hit enter? Notice you get a little arrow right there. So you can either put in a number that's to the left, or you can scroll to the left, and then you hit enter. Now guys, notice what pops up, what's called a right bound. So either scroll or pick a number somewhere to the right. So I'm to the right of it, that's good for me. I could pick maybe 2 or 3 or 4, anywhere to the right would be fine. Regardless, hit enter. And notice what came up, now you're telling the calculator there is a maximum somewhere in between those two values. Well guys, don't guess, just hit enter. And I end up getting something like this right here. Not entirely sure why it does this, but in actuality, everyone, that is 1. If you have something slightly different, regardless, that is 1. And so it's 1, 30. And that's what I need us to write. Now it should be noted, the maximum, of course, is the high point. It's the vertical component. So in reality, guys, that is the true max. The 30 is the max. The 1 is the number that produces the maximum. Okay, good. Now maybe we can go a little quicker here for letter B. Let's go get the minimum. And I'm hoping, just looking at the graph, you see that this would be a minimum right here. It kind of changes, it's going down and then going back up. So let's go back, let's do it a little quicker now. Everyone hit second and then trace. And you'll see, of course, the minimum right there. So let's go minimum. Now, again, it's up to you. I'm all the way over here, and actually on my board, it is really quite the pain to keep doing this. I like scrolling typically, but not always. And so if I don't like scrolling, I can pick a number just anywhere to the left. I'm just going to hit 3. And do you see? It just kind of gave me somewhere to the left of that. And then, notice it says right bound. Again, you can do the same thing. You can go to the right of it if you want, or you can just pick a number to the right. I'm to the right, so I'm okay, and hit enter. And look, you're telling the calculator there's a min in there, go get it. And there it is. Same deal, guys. Ignore that whole piece there. It is just 4. And so this would be 4, 3. And remember, when we talk about minimum, we're talking about the lowest point. Lowest is really a vertical aspect of it. So that's the minimum. The 3 is the min. The 4 is what produces it. Okay, great. Let's go do some intercepts on this. We'll be doing a lot with this. So the y-intercept, what is the value of x? So let's bring it back. I hope you see that the y-intercept is right here. Bunch of ways to get it. I'm going to just show you one right here. So hit second, go back to that menu. And in this case, you're going to hit the value for me, please. So just hit the value. And this is a nice feature because what it allows us to do is prompt the calculator to give it an x value, and it will come up with a y value. And so I kind of wrote it on your sheet here, what is the value of x on the y-intercept? And I hope you'd agree that the x value is 0. So I'm going to let x be 0, and notice what it did. It gave me the y value, and it put me right on that point on the graph. Kind of a nice feature, isn't it? So if you need a particular y value from an x, that feature really does nicely. So this would be, in our case, 0 and 19. Awesome. Letter D, find the x-intercept or intercepts of the graph, and it says what is the value of y. All right, nice. So I only see one x-intercept, happens to be this one right here. And there are probably a couple ways to do it. Again, I'm going to show you one. We're going to actually see this maybe the end of first semester, beginning of second semester, working with this. But to find the x-intercepts, it's not quite as easy. We do go back to that menu. We can't do value. Value only works if you give it the x, it gives you the y. You can't reverse it. You can't give it a y, and it would give you the x. But what we do is we go to this little feature right here, what's called the 0. And so the 0 of a function actually happens to be equivalent to the x-intercept. So now, guys, notice, same deal. We want to go to the left, then we want to go to the right. We need to tell the calculator where that 0 is. So I scroll, because right now I am to the right of it. So I'm going to scroll. Notice I am to the left now. I'm below, essentially. I hit enter. There it is. There's my left bound that popped up. Then, guys, scroll if you would. Scroll to the right. Anywhere to the right will do. And hit that right there. And then hit enter one more time. And notice this is when the y value was 0. And it gave us kind of an irrational number right there. I'm going to go ahead and ballpark this. So it's about negative 0.572, comma 0. So we've done max, min, 2 intercepts, different characteristics of the graph. That's great. Let's do the last piece where we talk about where the graph is increasing, decreasing, or constant. And in fact, just off to the side, when we talk about intervals and really analyzing it, we really talk about the domain intervals. So if you want to write that in place, that would be great. So all of our answers are going to be in terms of x. And so we would kind of read this graph going left to right. And as we go left to right, is the graph increasing or decreasing or constant? Well, let's go ahead and read letter E and then see what we can find. A function is increasing on a particular interval if the graph rises from left to right. Find the interval or intervals on which the function is increasing. Beautiful. All right. So I bring my graph right back up, and let's see what we have going here. I'm just going to hit that, clear a couple things out. And notice, you kind of see it's increasing. We hit the max, and then it starts to decrease. And we hit the min, and it starts to increase again. I hope everyone's all right with that description. And so what I'm envisioning is that the graph is increasing all the way up until this point right here, which would be, by the way, an x value of 1. We found that right here. It's decreasing in between these two x values, and then it's increasing anywhere to the right of this x value. Okay, so how do we want to express that? Let's see what suits us. So I hope everyone's comfortable with the fact that as we are anywhere to the left of 1, so from here, if you kind of envision this sort of a boundary, so to speak, anywhere to the left of 1, as I go left to right, the graph is increasing. Is everyone okay with that? So as I am anywhere to the left of 1, if I'm working left to right on my graph, it's increasing. Anywhere to the right of 4, the same deal. Anywhere, go to the right of 4, and as you go left to right, the graph is increasing. So to the left of 1 and to the right of 4. So I don't know, you can just put less than 1, but essentially I have this, and let me go ahead and not do it in interval notation here. Let's do the inequality. So I have anywhere from negative infinity all the way to 1. And if that doesn't compute, please let me know. Or anywhere from 4 to infinity. The graph would be increasing. Now, if you wanted to just write this piece, x is less than 1, that's fine. And if you wanted to just write this piece, or x is greater than 4, that's fine with me as well. But I would argue it's really those two intervals where the function is increasing. Now, decreasing, I think, as I had already alluded to, seems to be in between these two values right here, right? From 1 to 4, it's decreasing, just from there to there. Not sure if you remember how to write this as an inequality, but in between 1 and 4 means greater than 1 and less than 4. And we would write it like that. Nice. And in this case, if I look at part G, it says a function is constant if the graph neither rises nor falls. What that would have to look like, everybody, is basically a horizontal line. That's the only way it doesn't rise or fall. And so in this case, I do not see an interval where the graph neither rises nor falls. I've had students over the years say, hey, wait a minute, what about at this particular point it's not rising or falling? Or this particular point it's not rising or falling? And you're right, but we're talking about an interval. And I would argue an interval has to be in between two values. So you're right, as a matter of fact, and when you get to calculus, you'll explore that very idea that the graph is not rising or falling at this spot, but we're talking about in between 2 points. So anyway, I'm going to go with that right there. All right, let's move forward on the next two investigations. So investigation 2, graph the following functions, and then I'm curious what they have in common. So guys, I'll tell you what, no tick marks. Let's be quick with this. 4 coordinate planes, if you would. And what's kind of fascinating, even though those are 4 entirely different families of functions, quadratic, absolute value, quartic, trigonometric, what's called a sinusoidal, by the way, as a matter of fact, they all kind of fit in the same category of functions, and that's what we'll explore right here. So let's go ahead and do that. We'll be fairly quick on this. It'd be great if you can graph a couple with me. Go back to the y equals, if you would, and clear that out, and just type in x squared. After you type in x squared, can you hit zoom and number 6 for me? And there you have it, a nice parabola, looking good. And if you would, go ahead and just draw that parabola right there. Okay. Good. Absolute value 1 coming next. Go to the y equals. And what we're going to do is the absolute value of x. So hit math for me. So hit that one. Go 1 to the right. And there is absolute value hidden. So ABS, absolute value of x. And instead of the U-shaped parabola, we get the V-shaped graph right there. So let's see. There it is. Looking good. All right, 2 down. 2 to go. And let's see, as you're putting them together, I'd ask you this. What do all of these have in common? Graphically. And that's what it all is right here. What do they all have in common? There we go. I graphed that. An interesting one. Kind of flat on the bottom there. Not truly, but it does level off quite a bit. Yeah, something like that would do. Okay, I like it. And then the last one here, which we will explore second semester. Kind of cool. So what you're going to do is type in cosine of x. The cosine button happens to be right here. And then cosine of x. And it does say to hit a particular window. So the Z trig, so that's under the zoom button at the top. And we've worked a lot with that standard window. In fact, most of ours has been under the standard window. But there it is, Z trig. So number 7. And you get what's called a sinusoidal wave. Look at that one. That's pretty cool. Nice graph. And it looks something like this, give or take. Doesn't have to be perfect. All right, now guys, I need you to maybe pause the video for about 60 seconds and stare at that. And what I want to know is, graphically, what do all 4 have in common? Now, you might be right. You might say something like, oh, they all have a minimum or something like that. I don't know. There are a variety of things you can say that will be true potentially. It just might not be what I'm looking for here. So the question, I guess, again, is what do they all have in common? All right. Now, if you're coming on back here and thinking about it, I would ask you to use the idea of symmetry. That's what I'm after in this case. Symmetry. And what do they all have in common? Well, here's what they do. They have perfect, what we would say, y-axis symmetry. If I take half the graph and reflect it over the y-axis, it would reflect perfectly or land perfectly on the other half of the graph. This reflects on that. This reflects on that. Even this one, look at this one, guys, perfectly reflected over the y-axis. That is the commonality that I'm looking for here. And because that actually happens, these functions all fit into a particular category, which I will describe on the back. One more quick investigation before doing that, if we can. Here we go. So, 1, 2, 3, 4. And again, 4 different families. Ready? Cubic, quintic, rational, and another sinusoidal in the trig family. Okay, well, let's go get them here. Same thing, let's just graph quickly. We'll have to go back to our standard window for most of these. Clear that on out. Hey guys, let's go. X cubed. You can do it. You're doing great. X cubed looks like that. So something like this. Could have been better. Oh well, not bad. Let's go get the next one in the quintic family. So what do I have? 0.2, x to the 5th minus x. There we go. Not too bad. Looks good. Coming up like this. Down and then back up again. Again, you probably draw much better than I do. Next one. Here we go. Doing nicely. Just getting them down, graphing them. And then I'd ask you the same thing in terms of commonality. Here we go. Rational function looks kind of like this. Kind of cool. So 3 down, everybody. Let's get that 4th one in play. It'll look very similar to the one right above it, by the way. but a slight difference. So here's what I have. So here's your sign button, by the way, sign, X. And let's hit that zoom button again at the top and number 7. And again, it's similar. It's got that same little sinusoidal wave, kind of cool, but slightly different graph. Should look something like this. There we go. I'm liking it. So I would ask you the same thing. Take 60 seconds. Pause that video. And what do they have in common? Use the same premise, by the way, if you would. Okay, if you weren't sure what I meant by that, symmetry, guys, symmetry. What type of symmetry do they have? You'll have to maybe think back to your geometry class. Terms of symmetry here, but they have what is called origin symmetry. Each one of these graphs. And what that basically means is that if you were to rotate the graph 180 degrees around the origin, you would get the exact same graph. So it's not a reflection necessarily, it's a rotation. And so if you can picture this right here, it's tough for me to do with this pen, this rotates 180 degrees, this rotates 180 degrees, you get the same graph. It works here, it works here, look at that, that one's kind of cool. And even better, look at this one. This comes down, this comes around, holy cow, that's awesome. So it has what's called origin symmetry, all around that point right there, all around the origin. And because it fits that graphical commonality, these all fit in a particular category of functions. And let's go name them and play a little fill in the blank on the back. All right, here we go, guys. So the first set of functions from investigation 2 are categorized as even functions, even. I'll tell you basically where the name comes from in just a sec. So what do the function or graphs of even functions have in common? They of course have the y-axis symmetry. And here's what I'm going to ask you to do. What does that mean graphically? And then let's see if we can come up with the algebraic rule behind it. So here's what I'm thinking. You fill in the rest. See if you can pull this off. For each xy on the graph, ready? What else is on the graph? So you're going to have to fill that in also on the graph. All right, so I'm going to go back for just a second. Try to think abstractly here. And again, good graphical analysis. So these are all even functions. And by the way, if you kind of look at the polynomials that I put up here, look at the exponents. Do you see that they're even exponents? This would be x to the 0 on the back. So that's where kind of the name comes from. In the polynomial family, all of them have to be even exponents. Okay, now graphically. So if I have a point, x comma y, there's x comma y on there. What other point must be on the graph of this exact same function? Well, if you look over here, I see it as the opposite of x and the same y value. Does that make sense? Anywhere you go, if this is your xy, then very simply this would be the opposite of that x and the same y value. And that's, I think, what we fill in. So, and you could look at that. If you know some points on the graph, that should fit. Wow, very cool. Let's fill this out here. Even functions then can be identified with this algebraic rule. I won't make you really play this out too much here, but you should be comfortable with this, working with function notation. That's what this is all about. And so in this case, here's the algebraic rule. F of x should be the same as f of negative x. let me just show you why and how that quickly works, and then we'll go on to the next piece. So guys, look at that function, the one I gave you originally, x squared, right? I said it's even. Well, according to this, what that also means is that f of negative x would be the exact same. And we're going to play a lot with these. We've done this before. So the input would be a negative 1x. And I would ask you to remove the parentheses, of course, and think of this as a negative 1 squared and an x squared. And everybody, what is negative 1 squared? Well, negative 1 squared is 1. So you get 1 and an x squared, and there it is. So this is the same as this. And if that's the case, then it's even. Kind of cool. All right, you can probably guess what the next one's going to look like. The second set of functions are categorized as odds. They're odd functions. Okay, what do the graphs of odd functions have in common? Again, just kind of a synopsis here. You keep it up. They have what we would call origin symmetry. You'll do a lot of work when you get to trigonometry, kind of talking about odd versus even. All of the trig functions that you see will kind of fit in one of those two categories. So this means, same deal. Here's, I guess I would ask you, again, just kind of really think about it in detail. See if you can put it together. For each x, y on the graph, what else is on the graph? So go back and take a look. After you kind of jot this piece down, let's fill it in. What else has to be on there? So I go on back. Here we go. Here's the xy, just kind of picking an arbitrary point there. There is your point, right? What other point must be on the graph? Think about if I rotated this around 180 degrees. That would kind of put me down here. So what is on that graph? Well, I'm hoping you see the x would stay or change to the opposite, and the y would change to the opposite. And there you have it. And that works all the way through for any point. Pick any point, and its opposite x and opposite y is also on it. Okay, so fill it in. Negative x, negative y, also on there. And there are a couple different ways to express the algebraic rule. I'll go ahead and just do this piece right here. So odd functions. And here's the algebraic rule that I'll put together. Again, probably a couple ways to express it. I think that's probably the most common. So input, output, both with the negatives. Hey, let's just take a quick peek. And then I'll let you just kind of work with this graphically. So this, let's just do the x cubed. Now what it's basically saying is, for this function, if this is true, it just fits in this category, what's called an odd function, and would have this symmetry right up here. So for example, f of negative x, if I was to do that, that means the input changes to negative 1x, and negative 1 cubed, because this is kind of a negative 1 right next to the x, negative 1 cubed is negative 1, and x cubed is x cubed. There you go. Very nice. Now what happens when I do the opposite of f of x? That just means I put a little negative out in front, and do you notice, of course, they are the same. There they are. I'll circle them. This, when I did it, is equal to this when I did it. Because that's true, it's an odd function. That's all. It just fits that algebraic rule, and what it means graphically is this right here, and this is the symmetry that all those graphs have. Okay, cool. Let's kind of wrap this up pretty fast here. Let's see. I would love for you to pause and take 3 minutes. You don't have to do the algebraic rule. All I'll ask you to do is graph each of the 6, and you tell me, does it fit into the even category, the odd category, or neither? Obviously, you know, plenty of functions that just don't fit in either. All right. So let's see. I'm hoping at this stage you did it. If not, again, please pause and do it yourself. just look at the symmetry, guys. Again, you don't have to do the algebraic rule. I'll only ask you to go ahead and graph it and figure out. So here's what we would do. 0.3 x to the 4th. I zoom number 6, and let's try that one more time. Hey, that's interesting. Hang on. Okay, got it working there. So here we go. It's 0.3 x to the 4th. Take a look at that symmetry, everyone. Y-axis symmetry. This is an even function. So that one is even. Perfect. Again, my hope is that you've typed these in at this stage. You're just looking at the symmetry. So how about this one? 1 and then divided by, how about an x plus 3 right there? I'm going to hit graph again. Does that look like it has origin symmetry? No, not exactly. Y-axis symmetry? Nope. So I'm afraid that is a neither. And it does have 180-degree rotational symmetry, but it's around this point. It's not around the origin. It's rotating it around here, not the origin. All right, next one. Again, just graph, guys. No big deal. Getting comfortable with those calculators, getting quicker, getting more efficient with them. Type them in, hit graph, and it's looking pretty good, but is this reflected directly over the y-axis? Doesn't seem to be. Looks like we're more space here than here. So I would still say neither for this one. Okay, let's keep it going. Next one, guys, is x cubed. I think I see plus 1. And it looks like I have some good rotational symmetry, but is it rotated around the origin? To kind of move this down here, is it rotating around the origin? No. It's rotating around that point right there, everyone. And I'm afraid this is another neither. Neither. All right, so far. Actually, I have some answer blanks there. You can put them in those if you'd like. Okay, next one. Go back, and I get y equals x. Ooh, how about this one? It's kind of an interesting one. Bring this on down. Bring this around up, all around that point right there. That's the focal point. And I see this as having the 180-degree rotational symmetry around that origin. Looks good. So odd it is. And then, let's see, last one here, get this moving. Another absolute value. So I would do math, move it over, absolute value of 3x, close it, minus 1. I hit graph, and does that look like it has one of the symmetries we're looking for? I think so. I think it's got y-axis symmetry there. And because it has y-axis symmetry, it's even. Cool. Would it meet all of the algebraic rules? Sure. If I did the even rule on this piece, it would work. If I did the odd rule on this piece, it would work. I won't waste our time on that. Again, trying to pick our battles here. Just in terms of identifying odd, even, or neither, just graph, okay? One last piece, and then we'll wrap this up. Another type of graphical symmetry, relations but not functions, is what's called x-axis symmetry. So maybe a graph that looks something like that. So we did y-axis symmetry, we did origin symmetry, something like that. Notice, everybody, this is not a function because it does not pass the vertical line test. Hope everybody sees that. But regardless, it does have x-axis symmetry. And I'd ask you, the graphical analysis piece for each xy on the graph, what else would be on there? What do you think? So if here's an x and a y right here, here's the point, perfectly symmetrical with respect to that x-axis. And what would that ordered pair look like to you? Has the same x. I think the y is opposite. So something like that. And there you go. Okay. Again, we won't see too much of those. You will work with these next year in pre-calculus. relations but not functions. But for us, obviously, this does not fit in the same function category. Okay, great. If you have questions on these pieces, let me know, especially the technology. If you're having any issues with that, I'm pretty good about troubleshooting and can figure out what's going wrong. Well, thank you for listening. Please let me know if you have questions.